We know so much about biology nowadays, so why is it currently so difficult to figure out how to make a person live longer? I mean, we know how to do this in worms and often in mice, but why is the study of extending lifespans so hard in humans? Why are there so few companies studying this? And what is the future of longevity research? And what would it be like to live a much longer life? Welcome to Inner Cosmos with me, David Eagleman. I'm a neuroscientist and an author at Stanford. And in these episodes, we sail deeply into our 3-pound universe to uncover some of the most surprising aspects of our lives. Today's episode reaches beyond neurobiology to our biology more generally, and specifically about whether we could live a lot longer if we just understood which of the billions of tiny molecular signals in a cell mattered for the aging process, and which ones we could grab a hold of and tweak, and how the whole network might shift in a way that keeps everything young and optimized. It's often said that the only two certainties in life are death and taxes. But it turns out the third certainty is that people will put in a lot of work to avoid those two things. So today's episode is about the endeavor of living longer. This is not about immortality, in other words, never dying. Instead, this is about longevity, increasing your lifespan. So to introduce today's topic, I'm going to read a short story that I wrote some years ago and originally read on BBC Radio. I have been asked to speak here at the funeral of a 122-year-old. As many of you know, I have been asked to speak not only because of my expertise in the history of aging, but also because she is a distant relative. She is my great-great-great-great-granddaughter. Her death is tragic to us, not only because she has died so young, but because she was haunted her whole life by an incurable blood disorder and was well aware that she would not have a long life. I have been asked by her parents to perhaps ease the tragedy of her young death by thinking back to the time when a lifespan of 122 years was not considered short, but unusually long. At that time, not so long ago, it was not typical for people to earn multiple PhDs or to be citizens of multiple countries in their brief twinklings of a lifetime. They tended to mature faster, moving out of the house in their teens or 20s, having families of their own by their 30s, retiring in their 60s, and dying shortly thereafter. With only enough time for one career and one family, all things ran on an accelerated schedule. In each generation, they had to relearn politics. They had not experienced the patterns before. Everything seemed new. Every message of progress seemed inspired. Of course, this had one advantage. People did not burn with vendettas that belonged to distant times. Instead, they died quickly, and their children held different attitudes. Politics could take sharper turns. We all know what it's like to spot a forgotten lover a century later. But imagine what it was like to never achieve any meaningful temporal distance from your past choices. Everything you've done is there at your heels to haunt you. Obviously, our mistakes make life educational, but as we know, getting second chances allows us to endure it. People with rapid lifespans felt quite close to their recent ancestors because they only had 4 of them alive at best. We typically have 512 great-great-great-great-great-grandparents alive, enough to fill a good-sized lecture hall. Therefore, relationships sink to genetic interest rather than emotional salience based on scarcity. For those with only a handful of decades, the idea of staying with one partner throughout life was something to be devoutly hoped for, and people would declare that as part of their wedding vows. In modern times, we know of several couples who have celebrated 300-year anniversaries, but it's obviously much more common to enjoy dozens of marriages. As we mourn this loss today, we should remember that those with a scarcity of years had no shortage of one thing: novelty. For the rest of us, time speeds up as we grow older. At my age, decades pass like summers. We have seen life's patterns many times. We have traveled, we have married, we have wrangled, made peace, failed friends, impressed strangers, seen new groups rise and dwindle, sought new narratives about our abilities and our purpose. But in the end, as things become less new, we write down fewer memories. Unique experiences become increasingly scarce. And so, as we mourn this life cut short here today, we can be thankful that for her, at least everything remained novel. She did not drown in the ocean of time. Every day, she continued to find new seashells at the edges of its low-lying shores. Okay, so that was my short story about the social changes that would follow if we were to succeed at longevity science. How would that change our lives, our decisions, our traditions, how we spend our time? But today I want to ask, is longevity possible? Where are we in terms of the science? When you look at life expectancy at birth, let's say 200 years ago, you find that it was about 29 years old. At the beginning of the 19th century, even the healthiest countries in the world had a life expectancy no longer than 40 years. Now, in the 21st century, the world average is 73 years. That's a huge difference in just 200 years. Is it due to miraculous medical advances? Well, not exactly. Largely, it's due to simple advances like being able to control diarrhea and vomiting and having antibiotics. And also on the simple public health initiatives like sanitation and clean water and managing sewage. These are the steps that have had massive impact in the expected lifespan. So we've seen astonishing progress, but keep in mind what we're talking about there is the average lifespan. We prevented people from dying young, and that cranked the average up and up. But the longest lifespans, which are influenced by biological aging processes, they haven't really changed. People aren't generally growing older. In other words, 1,000 years ago, you could have lived until 85, and now you can live until 85. Despite all our advances, there seems to be an upper limit biologically in the low 100s. So at the moment, we haven't yet found ways to significantly slow or reverse aging itself. There seems to be a biological ceiling to human life, and this is presumably set by genetics and properties of our cells that limit how long the human body can sustain itself. This is despite all the improvements in health and medical care. But on the flip side, we're living in a time where there are a lot of studies with worms, with mice, occasionally with dogs or monkeys, that seem to indicate there may be molecular solutions, or at least helpers, to the problem. If you follow the field or simply scan the news headlines, you'll see articles about drugs like rapamycin or chemicals like resveratrol or approaches like caloric restriction. And what you'll see is that in animal studies, these seem to increase lifespan. So the question is, should you be taking these drugs and changing your diet? Do the studies translate over to humans? And what dose should you go for? Or how many calories should you restrict? Well, these are questions that short news articles tend to skate over the complexity of. And so to really understand the big picture, we need to talk to experts in the field of longevity. And that brings me to Martin Borch Jensen, a researcher who takes the position that if we can really understand the biological mechanisms of aging, that gives us our highest leverage for alleviating human disease. Martin got his PhD at the University of Copenhagen in aging research, then did a postdoc at the Buck Institute before becoming a biotech entrepreneur. He became the co-founder and chief scientific officer at Gordian Biotechnology, which is a company that puts the study of longevity at the center. So here's my interview with Martin. So what is aging biologically?
That is an unanswered question by the field of aging biology, right? So I think that's one of the core things here, that nobody can tell you, like, here is exactly how this works. You could sort of compare it to, like, what is society or civilization? What is the economy? It's sort of this complex thing where we know a lot of components and we know some key factors. But let's try to do our best here and say, aging is some set of changes that happen in your body biologically that worsen your capacity for your body to, like, restore itself to homeostasis is the technical term, but basically, like, your body is in a certain state, and then the essence of life is that when something gets it out of that state, it sort of restores itself, right? So if you drink too much, you have a hangover, your liver's going to work and so forth, and then you're going to be fine again. If you get influenza, you have an immune system that's designed to kill all of those viruses, and then you're going to be fine again. And so that's sort of the return to homeostasis. And I would say aging is a set of changes that happen that lower your ability to, like, return to homeostasis. And then over time, that combines with everything that you're going through in life to lead to, you know, your organs failing in different ways, and you get weaker and you get slower and, like, all of those kinds of things. So a set of processes that lead to all of the bad things.
And I once heard you say that if we were all 28 years old, we wouldn't have all these departments in academic research institutes and hospitals and so on, because we would just need to address a few things. I think you mentioned testicular cancer, a few other things, but we wouldn't need giant cancer departments, MD Anderson and so on, because these are all things that come along with aging.
Yeah, like if you just look at the incidence rate of a lot of different diseases, heart failure. How many people do you know who've had a heart attack, like, above age 50, and how many people you know that had a heart attack was, like, below age 50 or below age 30, right? And probably your anecdotal evidence there sort of aligns with just the stats we have, which is, like the rate goes up 1,000-fold or 10,000-fold or something like that, right? And so, yeah, when you are young, there's just a few things that affect you. And when you're old, there's a lot of things that affect you. And US healthcare spend is $4 trillion-ish. And, like, the majority of that fraction is for, like people who have age-related diseases, often multiple age-related diseases.
Now, when people go about trying to research this, it's limited in some way by the technologies that we have. And so what people have done over, let's call it the last 20 years, is they look for particular biomarkers. So tell us about that and how it's evolved in the last couple of decades, and what you're doing, leading to what you're doing at Gordian.
Yeah, absolutely. So the field of, like, hey, we can molecularly sort of study and manipulate aging is really only about 3 decades old. In the early 90s, there were some studies where researchers changed a single gene in some worms, and it made the worms live twice as long. And so before that, it's like, well, what is aging and can we really change it and so forth? But this shows that there is a way to regulate the aging process that's already innate in sort of the way our biology functions. And so that's cool. And so in a worm, it lives 3 weeks after you extended the lifespan, right? So you can do studies where you're just like, does it live longer? Is it healthier? As you get closer and closer to humans, that's sort of impractical, right? Like aging by definition takes a lifetime. And so you don't want to do 40-year studies all the time. And so people have done a couple of things in response to that. One is like find some area of biology that like this seems important. This accumulation of these senescent cells or these particular changes in your body seems important. We're just going to study them and then sort of like trust that they are important for the aging process. The other thing people have done is try to find, they're usually called like aging clocks. And so it's something that you could measure that when you look at it over time, it changes with age. And so you can use whatever the measurement is to tell you sort of like how far along is this person, right? If we do an analogy to a company, maybe it's like you try to schedule a meeting with someone and whether they can take the meeting and like it's a young startup, you can take the meeting in the next 45 minutes. And if it's like a giant 100,000 person company, it's going to take you a month and a half to. So that's like a marker of the aging of, in this case, the company. So we have those, we have multiple of those for sort of human aging. We don't yet have one where that when it responds, that's actually our aging changing versus it's measuring something that happens alongside aging, but it doesn't necessarily mean you're better off if the number goes down. So that's sort of the main limitation here.
As in, I do something so that at this large company, I can get a meeting quickly, but it doesn't change the age of the company. It's still an old company, even though I did some tweak to make the meeting happen.
Right. Like you could set up so that like every Calendly in that company must auto accept a meeting immediately. However, the company's ability to actually act on what happens in the meeting is not changed. The amount of bureaucracy is the same. And so you could optimize that one all you want, but it doesn't really do what you want it to do.
So the point here is that even if you do something that changes these biomarkers, your cell might be just as old and, having all the ills of senescence, even though you think, hey, I fixed it.
Yeah, like let's say, for example, a lot of these are blood tests, right? So they would measure stuff in immune cells primarily because those are the ones circling around your blood. And so imagine if, and your immune cells will go, and then when you have an infection, they'll divide and proliferate and create more that target this infection and so forth. Imagine that what a given aging clock measures is actually how many times has this cell divided. That will tend to go up as you age, but whatever like TikTok tracks that, it's not the whole aging process. There's all this other stuff going on in all these other organs. And so I think that's the key thing that sort of currently we need to address with these kinds of aging clocks before we can really reliably use them to accelerate the research, is how specific are they for predicting the changes that we want to use them for?
And I know that like everything in biology, what we're looking at are these vast networks that bankrupt our language. They're so complex. And so what we've been doing over the past decades is looking for little places in the network where we say, aha, this is maybe the sign that we need to read, right? But what's your approach to this, which I think is very clever?
Yeah, absolutely. So I spent, after this sort of existentialist phase, I went into academic research. I did a PhD at an aging institute, and I did postdoctoral research, and was sort of heading on the academic track to be a professor, all like trying to figure out how does this work? Because like one approach to fixing a system, let's say a car or whatever, is like, okay, well, I understand what each piece does and I can see where the broken thing is. And then I go in and I like fix that broken thing. So that's one approach, which makes sense if you can like get to an understanding in your lifetime. And so if you sort of capitulate on that, which is honestly what I did, it's like there's so much biology. Like we don't even know what we don't know yet, right? How do you find a solution if you don't have an understanding of the whole? And that's why the company I started with my co-founder Francisco, it's called Gordian, after the sort of legend of the Gordian knot, where you try to untangle it, but it's so complicated you can't untangle it. And then Alexander, the then not yet great, decides to cut through it instead and find an elegant solution that questions the assumptions. And so the biology version of that for Gordian is, I had a knowledge of how complex everything was. And I knew that, we don't actually know what aging is. I can't give you, here's an accelerated version of aging that captures all the important parts because we don't know all the important parts. And so if we want to find treatments that work for different age-related diseases, and this is really important because, like we were talking about before, if you just look up top 10 causes of death in the US, 7 of them, aging is the number 1 risk factor. And the 8th one, like diabetes, it's number 2 after diet, right? And if you just look at our spend, what are the things that we can't cure? What are the things we're worried about? It's not tuberculosis anymore. We did good, but it's all these age-related diseases. And so we've put a lot of money into trying to treat these diseases and find effective medicines, but we haven't succeeded at scale yet. Maybe that's because these diseases, as we talked about before, they manifest in old people. And so some of these physiological changes that are happening with aging are critical for the disease, being able to manifest and not being just repaired. So if we do all of our drug discovery in organisms that are young, let's say, some model organism in the lab that is young, and we've sort of engineered it to get the disease. Let's take Alzheimer's. People often have these animals that have express the mutant proteins involved in the disease.
These are mice, for example, you're talking about.
Yeah, exactly. And so we take these mice and we say, let's find every mutation that happens in Alzheimer's patient and throw all of them at the mice, and then it's going to get Alzheimer's really quickly. But it's not really Alzheimer's. It's one specific dysfunction. And then we can fix that. We have good drugs to treat that in mice. We don't have good drugs to treat Alzheimer's in people because it's probably more complicated.
Because the rest of the adult human has 5 million other biological issues going on at the same time. So those mutations in the giant network that's happening, you get different results than you do in a mouse who is otherwise young and perfect but has these mutations.
Yeah, that's right. You get a flat tire, driving to work. It's fine. I can deal with this, right? But you get a flat tire, driving to the hospital with your kid after you lost your job. It's you don't have the capacity to deal with this thing anymore. That's probably a lot of what happens in these age-related diseases, that things aren't working as well. And so you don't have the capacity to compensate for whatever is going wrong. Here's where we are. We've studied these diseases. We've forced ourselves to use these simplified models of the disease because it's just we didn't have a practical way of trying a lot of things otherwise. And then we failed. And so Gordian says, well, what if we had a way to go into the most realistic environment for the patient? What if we could, instead of making this disease in an animal model in this accelerated way, what if we could find an animal that has the same disease as the human and developed it over a long period of time, the same way that humans do, and then we could test a lot of things there. And so, for example, we could work with, for osteoarthritis, which is one of the diseases that we're working on. A lot of people have these young mice and you do surgical injury and whatever. We can find a horse that got osteoarthritis from running around and living life. And then we can go in and see, can we treat the osteoarthritis in this context? And it's much more like a human. It's like an avatar for the human patient. Now, anyone could do that. Anyone can go find a horse somewhere on a farm and then do this study. But the way that most studies are done, you have these large groups of animals with treatment A and large group of animals with treatment B so that you can compare across the biological variability of the individual animals and stuff. That's just impractical. It's possible, but it's prohibitively expensive and logistically challenging. And so Gordian started with the idea that we can actually do this if we invent a way to test hundreds of treatments in a single animal. And so that's the core of the company. We can go into the most predictive system for, is this going to cure disease X in a patient? And then we can test a lot of things there. So we don't have to be very smart. I try to design it so that I can be not very smart and still succeed. And so the way we do that, there's a lot of cool biotechnology, and we have these re-engineered viruses that can deliver therapies to individual cells of the organ, and then we can pull those cells out and measure the activity of every gene in that cell, and then predict, okay, what does this these gene changes mean for physiology. So there's a lot of sort of hard stuff in actually making that work. But the core of it is find the thing that will actually predict the outcome you want, not something that you sort of hope would predict the outcome you want, but it's kind of very indirect. And then do a lot of research there. And so we're using that to find new treatments across 4 different diseases of aging: heart failure and fibrosis and osteoarthritis.
So the key is you're looking at lots of things at once instead of saying, hey, here's our single measure that we're taking from these horses.
Yeah, there's 2 things. We're looking at lots of different potential treatments, right? And so it's not like 3 decades of research suggest that this is the right target to treat this disease, which is often how it happens, right? And like what we've had to do and what I was just too impatient to stay in academia and do, right? Instead, we say like, well, let's test this like 100 different hypotheses, all in the same animal. And then the test is, measuring lots of things at once to see what is the overall like state of this cell. It was in a tissue that had, let's say, osteoarthritis. It was a chondrocyte, which are the cells in your like cartilage of your joints. And it's in this tissue that has all the bad stuff going on. It's got maybe some metabolic shifts that happen with age. There's an immune system and all this stuff. And if we take this one genetic target and turn it up or down, does it now resemble a chondrocyte that is in like a healthy horse, or has it changed in its behavior to produce more cartilage, which is the problem? So we can look at the full sort of state of the cell and we can say, is this the state that we want to go to in a way that doesn't require us to make a single hypothesis around this is how the disease works. So neither on the like, how do we try to poke it, or on the like, is this better? Do we rely on just like a single thing and like this is the way of the disease, because that's risky. Like we've done that, neuroscience very well.
Yes. That's the way that biology is having to move, because we've spent so long looking at individual pieces of very complicated networks, and we've seen the ways in which that doesn't get us the answer we want. Let me ask you a more general question, because you're an expert on aging research more generally. What do you see in human longevity in terms of, people are doing intermittent fasting and caloric restriction, and there are drugs like resveratrol and others that everyone's very interested in. What's your view of the field as it stands right now?
The key thing that we're missing is that measurement, right? And so if we had something that we had really validated, and by validated, I mean something along the lines of like, okay, I'm postulating that this thing will predict whether your risk of getting any disease, let's say, or your risk of like dying before a certain age. So I'm postulating that this measurement, your DNA methylation clock or whatever, like predicts that. So then we should test it, right? You should put a bunch of things in, at least in mice, right? That we know will extend mouse lifespan, and then a bunch of other things that like we know won't, and then see just how accurate are your predictions. If we had something like that where we're like, oh yeah, this like has great accuracy when this thing moves per our previous conversation, that means you're healthier. Then we would have a much better sense of like, okay, is this resveratrol thing working? Is this rapamycin thing working? Is the fasting doing something? There are a lot of sort of attempts to, like, people who have this vision that like, look, we should really get away from what is currently called healthcare, but is more like sick care, right? Like wait until you get disease and then get drugs for that disease. Towards a more like, can we just like measure your overall health and your, homeostatic capacity, your biological age, whatever we want to call it, and try to prevent you from having these diseases in the first place. That certainly, if we can do that well, that's a much better approach. It's cheaper, like ounce of prevention, right? And the tricky part of doing that is knowing the future, right? So we need to build these tools that allow us to know the future. Because currently, the other way that we do that is sort of controlled clinical trials, where you just like run the experiment and you have a bunch of people and then you randomize them to different groups, treat one and not the other one. And then we see, do we get the outcome that we want? But doing that for aging, it both, like if you're doing that for like, do you live or die? It takes a long time. It's fairly expensive. And in the US, it's not obvious, like, is that something insurance covers? kind of should be, but like we haven't really figured it out. So there's some financial risk involved there.
What's your intuition? If you're even looking retrospectively, I don't know if there are groups of people who have had resveratrol their whole lives and others that haven't or whatever, but when you look at the data and look at the whole picture, what do you feel is the thing that maybe you would do that might be useful?
Yeah, I think if you look at that, and then the other thing you look at is like all the animal studies, right? So like what actually makes a mouse live longer? And the answer is caloric restriction of some sort. So limiting the number of calories, or rapamycin, which is a drug that's used as an immunosuppressant. It's FDA approved at a high dose. So at a high dose, it prevents your immune system. It reduces activity. And so we use it for like organ transplants. That's not going to make you live longer, suppressing your immune system, right? But so at a much lower dose in mice, there's some recent data in monkeys. And there's a trial ongoing in dogs called Triad, where people are giving rapamycin to dogs and see if they live longer. Rapamycin has the strongest data other than this like eating regimen thing, especially for caloric restriction. There's a caveat of like, well, how much restriction? And how much restriction, once you multiply that by like how much do you exercise, right? Because it's like in the lab mice that generally are in cages and they have ad-lib food and so forth, you'll get a certain response. But then when people are very different, they don't have the same genetics. What is the right amount of restriction? There probably is some amount. I mean, there's literally, for everyone, there's definitionally some right amount. For probably a lot of people, it's probably lower than where we're currently at. But it can be, like there's a U curve. If you just eat less and less, it's definitely going to be bad for you. So that's where we're back to like needing a measurement. Rapamycin is the other one. But similarly, like too high a dose is bad. And so finding out like what is the right dosing here where there's actually a benefit, that feels tricky. The nonprofit I started has funded some clinical trials of rapamycin, like early stage trial, phase 1 trials for different. There's one for like reproductive health. There's one for oral health.
And this is in humans?
That's in humans, yeah. So there's 4 different trials that we funded, and I think there's 3 others.
And so you won't know the longevity piece for several decades.
None of those will give us the longevity piece, right? So I think at that point, you're looking at this dose seems safe and has a beneficial effect on this disease, potentially. And so if we then extrapolate like a broader health benefit from the animal studies, your like expected value of this might go to positive. But it's also possible, like it's still unclear. Yeah. So those are the 2 with the strongest data. Then there's some other things. Metformin, which is a diabetes drug. There's a lot of push for that. Like we should do a trial here in humans. There's a not yet started, but sort of like they're trying to fundraise for it, thing called TAME, TAME. And the metformin data, it's more sort of observational, what you said. Like, okay, well, we've given this to diabetics. So we have like tens of millions of person years of data. What that certainly tells us is like, this is not super dangerous. What it may tell us is like, oh, there might be lower overall cancer risk. But it's hard with these like retrospective studies because you always have to be sure that like the people that we looked at, was there some unintended way that we selected for certain people that already had a lower, risk of having cancer diagnosis and compared them to another one. So there's big caveats. That's why we do these trials. But there's some sort of human stuff. The animal studies are less clear on like metformin doing a whole lot, but might still be beneficial and probably is safe.
What do you do personally? Do you take metformin or rapamycin?
I don't take rapamycin yet because I'd rather have somebody else find the safe dose, right? I mean, the basic stuff you already know, right? It's just like you should exercise, you should sleep, you should like eat less bacon and more vegetables, definitely eat less sugar, right? So like most people, it's boring. I think like optimizing for the longevity hack right now, you'll get a bit, but like the delta between I'm a hardcore like longevity biohacker and I'm just like generally healthy, maybe it's 3 years or something. Like I think the much more important mission for the field is like, let's put our effort into doing these technological advancements that allow us to measure things, that allow us to test more things at once and like really try to solve because like we know there is potential. We know that like you or I could have a kid that's like 0 years old. So like one cell in your body has the capacity to create a functioning, completely non-age system, right? And we also know that there's animals that live much longer than humans, and there's great variability in like how long different animals live. And we know that we can like, genetically engineer this worm or this mouse to live longer. So we know it's malleable, we know it's doable, and it's possible to have like a big effect. I don't know how hard it is. Like, I don't know if for like 15 years we'll have some tremendous results with partial reprogramming or something, or if it's like, it's actually much harder. It'll take longer, right? Sort of like AI. It's like, it's just around the corner. And then suddenly it takes off.
So if we were to fast forward to 25 years from now, where do you think the longevity field is going to be?
Where I hope it would be is sort of like rigorous testing of aging clocks happening in the next couple of years probably will reveal many things to be fixed. And then like deliberate efforts to create these sort of like biomarkers. And then I think that's very doable on like a 5-year horizon with concerted effort. Not guaranteed that that would happen, but there are different actors that could like make that happen, such as the Altos Lab startups or ARPA-H in the US or Evolution in Saudi Arabia. So that's one. Or even, frankly, like private philanthropists. Like this is sort of like a seed stage startup level effort or maybe a bit more. So that's one. We definitely need that. Then we need to figure out, okay, what is the clinical trial we're going to run? Are we going to try with the current round of things like rapamycin or senolytics? People are excited about metformin. Got to pick the right thing or do a portfolio and then just start to run those trials. And then I expect, this is what happens in drug discovery in general. You try to run the trial and then you find out, oh, some of my endpoints, like we're not sensitive enough or whatever. So we could do another round of trials. So I think those things should happen. That's sort of the ecosystem. And then at the same time, people are trying to do drug discovery for targeting different mechanisms of aging. So if we did things in the right sequence, and this is sort of like, okay, emperor of the world, you you can like PM it all to like work out. And then there's reality, which relies on all these incentives and whatever. But like all the companies now, and there's more and more of them that are trying to find like age-specific therapies. Those would then have an outlet to be not just we're going after. And so what happens now is like, if I find a drug for aging, let's say I'm at Stanford, I'm doing a bunch of research, I have this cool thing, I think at least, and then I start a company and then we raise $50 million and we're going to go into clinical trials. BioAge just IPO'd yesterday. That was from Stanford. So that sort of fits the story, right? And they have clinical trials going. But even though the company started with like, we're looking at aging, they had the sort of incentive constraints to like, well, we don't know how you run an aging trial yet. So everyone is like, if we want to succeed here, if we want a good readout for the investors, for the patients and so forth, we're going to narrow down to like a specific disease of aging. And so you run that trial, which is good. Like, I hope that treats patients. One could imagine, and again, if we're being just blue skies ambitious, one could imagine that the US decides, look, we're doing this sick care thing. We have like 14 different institutes and medical specialties and all this kind of stuff. But there's clearly biology that spans those, right? Like when your immune system dysfunctions, there's a whole bunch of diseases. There's inflammation and stuff that like affects a whole bunch of diseases. We should stop doing these trials where we test for one drug, one disease, right? Match one of like 30,000 things to one of 8,000 diseases, and then try to do all by all there. You will take infinity time, right? Instead, we should develop ways, and again, this is sort of like an ARPA-H kind of thing. We should develop ways where when we run one trial, we can take some blood samples, and then we can look for these markers that imply that the drug might work on a bunch of other diseases. And so we sort of turn each trial we run in this country into something that has like an integrated overall beneficial effect on health, or doesn't, right? And so if you took that approach, you could have fewer trials that lead us to a portfolio of medicines that have a bigger overall impact. There's various reasons why we're not doing that yet. One, we don't have those measurements, right? So there's technological development needed to do it, right? Another one is we probably don't have the perspective, right? Like, again, we're used to, you have one disease. And like, that's the thing that the unit of sort of like medical care. And then another one is the way that the FDA is set up. It's sort of like nothing bad can happen, but slowing things down has a secret cost of like lots of people dying or whatever, but like nothing bad can happen. And so you imagine if you measure like, is this good for all these different diseases? Well, what if one of them is bad? What if this drug like will prevent Alzheimer's and heart failure, but it increases your risk of cancer by 10%? That might still be like a good deal for a given human patient. And you could also further segment down to people who are not at elevated cancer risk, like this might be extra good for them. But it's a tough sort of political decision to say this is, we're utilitarian in our healthcare or whatever. That has not been made, and consequently, for a pharma company or whoever's running the clinical trial, there is a disincentive to have anything look bad, because that might tank the whole thing. Even if like you get, like twice as much good stuff, but some bad stuff, that's probably bad news for approval right now.
So let me ask you something about this issue that you mentioned about looking at one disease at a time. If you were extrapolating, 50 years from now, do you think that the names of the medical professionals will change? So we don't have a neurologist and a cardiologist and a liver specialist and so on, but what we have are things that are more general or broad?
Optimistically, yes. Pessimistically, I feel like we will add something new and just sort of like staple in on top of the old. So you'll still have a neurologist and so forth, right?
If you were in charge, if you were czar of the hospital system and could say what it should be, what kind of things would you set up?
I mean, I think I probably would, yes, it's not like throw away all the old, right? Like you still have a heart. And like, if we want to know what's going on, someone who knows a lot about the heart and can talk in detail about the exact rhythm of your heart and what that means for like your chambers and stuff, like that is a good thing that we want, right? Then the question is like, what do we want to lump and what do we want to split, right? Like, what are the things that we've called different things, but actually they're a similar thing, right? And then what do we want to split up? I think one thing for sure we want to split up is like Alzheimer's and aging. So if you look at the National Institute on Aging right now, something like half the budget is earmarked for Alzheimer's research, which is like brain specific and just one specific disease, right? And so it's something that a lot of people are very afraid of. And so that's why it happened, right? But like, it doesn't make sense that like, that's just like lumped in under aging. So I think the things to me that strike me as like, there is a multi-organ thing going on here. For sure, like inflammation, immune function. And so we obviously have immunologists and we have people that look at like the function of the immune system. But the overlap between the state of like infections and then the amount of inflammation you have and like aging and the amount of different organs, like solid tissues and the amount of inflammation you have and like the interplay between those, that feels like a clear, something we're probably overlooking. I mean, COVID is sort of a big boost here where people are looking at like, okay, exposure to this virus, what does it do in the long term? And a lot of us, especially when we're young, right, we're used to like, okay, got cold, immune system killed cold, we're fine. It's just like, it's a separate class of things. But more and more evidence, like it does affect your chance of having Alzheimer's, like your amount of bacterial, like mouth bacteria correlate well with risk of Alzheimer's. It seems like, more research. So I think that's one. And then like, if we just think about like what goes wrong in your tissues, there's sort of some common things that happen. One is like an out of control inflammation loop that leads to fibrosis. So this is sort of scarring of your tissue. And this will happen in your kidney, in your heart, in your liver, in your lungs. And sometimes we call it like pulmonary fibrosis or COPD, chronic obstructive pulmonary disorder. So like smoker's lung. That's when it's real bad. But the process is happening in like most of your tissues at all times. So that's like a thing. What is this particular loop of something is like misfunctioning in the cells of that tissue, and then it triggers immune infiltration, and then that triggers fibrosis. Like that could be something that people are specialized in, which is true in academia. There are people who are like, look at that specifically, right? But in medicine, it's like different. Because then you start thinking, okay, we have this drug. Might this drug actually improve multiple organs, right? Because the same thing is sort of happening. Or maybe like this drug, it was approved just for this organ, but it won't work in this other organ because like the biology is a bit different. So those are some. And then there's the whole like, why do we lose cells? So there's a whole bunch of organs in your body that lose cells. The most shocking one might be like the thymus. And so the thymus here is like where your immune cells get told, like what should you attack and what should you not attack. And that whole organ is like basically replaced with fat by age 40. So it's just like you have an organ that you start out with and it's gone. Obviously, for women, like your reproductive organs, like you get this. And for men, I don't know if you get it, but that's one. Then there are other organs, right? Like your brain. You lose cells in your brain. You lose cells in your muscle, also gets replaced with fat. So there are some organs where like the way they fail is that you lose some cells over time and they don't get restored because that organ, the cells don't really divide. Like the cells in your brain, very little, muscle, very little. And so that's another area where there's like something that happens consistently across tissues that isn't covered by a single like medical specialty.
So let's say we extrapolate 1,000 years from now and all of the mysteries of biology where we're now sort of at the foot of the mountain. We've summited the peak and we're there. We understand the whole network computationally. It's all worked out. My question is, do you think there are natural limits to how long the human body can live? Or is longevity something that has no limit to it?
If you make no changes whatsoever to the human body, then yes, it does seem like there are natural limits, right? Like few people live over 100 and fewer still live more than 120, right? But that assumes that we don't change anything, that we don't have any technology, right? And so if we have endless technology and we are willing to change to some degree, like what is a human body, right? Like we're willing to, which we do already, right? So like if you lose a leg, you get robot leg, right? You have a cyborg now, right? And similar if you have a pacemaker, it's less visible. And so I think so far we're okay with some cautious pace of like, we are actually augmenting the human body in order to avoid disease. Even a vaccine would fall into this category, right? And so if you put that in, I don't think that there's any limit to some definition of the human body. And we can see that because like the human race exists still. And so many generations of humans have produced a new body out of a single cell, out of the same DNA code, right? Like life happened once and it's still going for many, many millions of years, right? And so it's not, and we see you have a tree that lived 5,000 years. That's a very different kind of body, but like it's possible to set things up to last that long.
And do you see any ethical or philosophical issues about what that would be to have a lifespan of 200, 300, 500 years?
Yeah, for sure. I mean, I think there's a lot of stuff. And I think that the not very serious version of engaging with that is like, it's weird and unnatural, and we need to like just not do it. Because by that argument, if you look at, I can send you like this graph of like lifespan over time. And so there have been these statements that like, well, it can't go above 70, it can't go. So you have these like horizontal lines, and then you just have like a straight diagonal line just going up since, hundreds of years of like, human existence or human civilization, right? So anyway, like, if you want to take the stance that like living longer is bad because X, and there's lots of different X. There's like, what if bad people live longer? What if a tyrant lives longer, right? Or like, what if we have wealth inequality and then it gets perpetuated for longer? Some of those are like, well, like we have inheritance so that it does anyway or whatever. But even if like that's a legitimate issue, I find it fundamentally not serious that your proposal is to kill everyone. Right? Like let's pretend that we had 300-year lifespans. And then we found that like, we have a lot of wealth inequality because the ones who get ahead early, they accumulate more and more over time. It's like, let's kill everyone at a young age is not a serious solution to this. Like, let's find a societal solution.
Philosophically, what does it mean if we're all living 300, 500 years? What does that mean for society?
There are concepts that we are used to working a certain way that might not work that way. The most obvious one is retirement, right? So like retirement is fundamentally like we recognize that humans are like not very capable, then become capable, and then are less capable again in old age, right? And so then we've structured society so that the ones who are most capable are supporting the ones who are not capable, including children, including infirm aged people, right? And so that's just like the way things are. And so obviously, if the older people, like if you just stretch that period of like competency, good news is that you don't bankrupt Medicare, which is what's going to default happen now, right? But of course, it means like you're not going to retire at 60 or 65 or whatever it is, right? But let's say we really extended lifespan. You live for like 300 years. You might have multiple careers in different areas. You might have like a work for this long and then go on like retirement sabbatical thing where you just like go back to learning a new thing for 10 years and you're not very useful again because like you used to be a scholar and now you're going to be an artist or whatever it is, right? And then you come back and you do a new thing. It'll be interesting to see what happens, right?
That was my interview with Martin Borch Jensen, who's a longevity researcher and co-founder and chief scientific officer of Gordian Biotechnology. And one of the things this conversation surfaces is why the science is so difficult. Biology is full of feedback loops that cause nonlinear responses, and that makes it really difficult for us to move from simple experimental observations like the blood level of some molecule type that we measure in worms or mice to reliably producing meaningful physiologic changes in humans, or even knowing what the right change is to aim for. So how far are we from a world where anti-aging therapies are as routine as vaccinations? It's not happening anytime soon. But on the other hand, we now have billions of young brains on this planet getting great educations. And with the exponential pace of technology and the increasing pace of medical innovation, maybe we can get there. Maybe we can not only prevent people from dying young, as we have done over the past couple centuries, but also extend a healthy lifespan such that we actually will someday give heartbroken funereal speeches lamenting a person dying at the tender young age of 122 years old. Perhaps we will come to understand the giant biochemical puzzle of ourselves and actually be able to shift around some of the pieces. Perhaps a few of us listening to this podcast may just be lucky enough to live to see that day, and therefore to see lots of days past that as well. Go to eagleman.com/podcast for more information and to find further reading. Send me an email at podcast@eagleman.com with questions or discussion. And check out and subscribe to Inner Cosmos on YouTube for videos of each episode and to leave comments. Until next time, I'm David Eagleman, and this is Inner Cosmos.